I could have sworn I had the lecture. All right. Getting to the lecture here. We are going to today review for Exam 2. Exam 2 over chemistry. Because it's a review, there's no clicker questions and there's no potential test questions. So it's just making sure that you have this stuff in your head for the exam. So, Chapter 12, when we introduce atoms in the periodic table. You'll have a copy of the periodic table, so no point in trying to memorize all of that. I mean, no point for the test. It's kind of useful to know where things are, but you don't have to. But you need to know these things about the atom, that your atom has a nucleus that contains protons and neutrons, each one of those things having about the same mass. And so we define the atomic mass unit to be roughly the mass of a proton or a neutron. And protons have a positive charge. Neutrons have a zero charge. Then you have an electron cloud of electrons orbiting around the nucleus. The electrons have a very low mass compared to protons and neutrons, so they pretty much don't affect our calculation for the mass of an atom. They have a negative charge. The size of the charge of an electron is the same as the size of the charge for protons, just one's positive, one's negative. And for a neutral atom, you'll have the same number of electrons as you have protons. Know about those electron shells, right? The first period is filling shell 1. The second period is filling shell 2. Third period, shell 3, and so on. And now this one here is a little more tricky, the difference in atomic number versus atomic mass. They both have that atomic thing in there. Mass is telling you about the mass. What two things in an atom have pretty much the same mass? Protons and neutrons. So the atomic mass is the total mass or the sum of the protons and neutrons in units of atomic mass units. Now, it's not perfectly true, that last statement, but it's pretty close. For our purposes, we'll treat it as if it is. So the atomic mass is the total mass, which you simply calculate by adding the protons and neutrons. On the periodic table, the atomic mass is shown. It's the number there in the circle or the bottom center. And you'll see it's not an integer number, even though you have an integer number of protons plus neutrons, and that's because it's not exactly the same. The atomic number, on the other hand, is the number of protons. The symbol for the atomic number is Z, and that's the number of protons. The symbol for atomic mass is A, and that's the number of protons plus the number of neutrons. Now, jumping forward a few chapters, the atomic mass was measured in what units have I been saying? Atomic mass units. Pretty simple. The atomic mass unit is the atomic mass unit. If we wanted to convert from atomic mass units to grams, we've learned recently about the mole. The mole is the number of particles that will make an atomic mass unit come to a gram. That is one Avogadro's number, because a mole is Avogadro's number of molecules. One atomic mass unit times Avogadro's number is 1 gram. So if I have a mole of hydrogen atoms, that one atomic mass unit for the hydrogen atom will have, if I have a mole of them, a mass of 1 gram. So the conversion from the atomic mass to the mass of a mole is very, very simple. It's 1 to 1. Just changing from AMU to grams when I change from atoms or molecules to moles. Okay, then for the periodic table, like I said, don't memorize it, but you should know these groups. So group 1, or column 1 as I called it here, are the alkali metals. Group 2 are the alkali earth metals. Groups 3 through 12 are the transition metals. And then don't worry about the next few groups. Don't worry about the chalagens, but do worry about the halogens. So group 17, the halogens, that's the ones with fluorine, chlorine, bromine. And then group 18, the noble gases or the inert gases. And you should know basic things about these things. Alkali metals, they're in the first column. What's special? What kind of behaviors do you know for the first column of the periodic table? Let's look at certain things. Valence, electronegativity, and size. Okay, the first column, they tend to lose an electron. Their valence is 1. They have 1 valence electron, and they tend to lose that easily because when you have a complete shell, that's really stable. If you're one away from a complete shell, it either will want to grab the extra electron to reach complete shell or be happy to give up that electron that's extra beyond the complete shell. So the first column has 1 extra beyond the complete shell, so it's happy to give it up. So it has that valence of 1. It's happy to give it up, so it has a low electronegativity. The electronegativity is how strongly it's holding on to an electron. And then the size. Excuse me. The size is fairly large for things in the first column. If you go to the second column, what's its valence there? How many electrons does it have that can bond in the second column? 2. Electronegativity is still going to be low, but a little bit higher. And its size is a little bit smaller. Now we get over to the halogens, fluorine, chlorine, bromine. What's their valence? They have 7 valence electrons. So how many bonds do you expect to form if you have 7 valence electrons? One more, so that you'd have 8. So you'd expect 1 bond if you're in the halogens. Oxygen, sulfur, the halogens, those have 6 valence electrons. So how many do you expect those to form for bonds? 2. Go over to carbon, 2 more. 4. 2 people put that for the potential test question yesterday. So the halogens, their 7 is their valence. They would like to have an 8th because an 8th would complete that last shell. And so they have a very high electronegativity. And because of that high electronegativity, they're really holding on to their electrons. They're small. Those are the ones that are most important to have in your head. Then we have a couple more things here. The noble gases, what's the valence for a noble gas? 8. Does it want more electrons or does it want to give up electrons? Or neither. It just wants to stay. Did you say it's full? Yeah, it's full, so it just wants to stay. So I don't even know electronegativity numbers there. They're inert. They want to hold on to their, I shouldn't put 0. They want to hold on to what they have, but they don't want any extra ones. They just don't do anything. So I don't know if we talk about a number there because they don't do anything. And their size, my recollection is they're fairly large again. Then finally, the transition metals. The transition metals are kind of unique. When we talk about the valence there, it's going to be a little odd. So we didn't really talk about the valence of transition metals. Their electronegativities are going to be scaling with where they are on the chart. So the farther to the right, the higher the electronegativity. farther to the left, the lower the electronegativity. So make sure you have that knowledge about the periodic table. You should be able to find where the atomic mass is, where the atomic number is, and so on from the periodic table. Final two things from chapter 12. Know what a quantum theory means. What does quantum mean? As used in the quantum model. Okay, we don't seem to have answers, so I'm going to tell you. Quantum means that you have only specific levels. So the quantum model, as we understand now, says that our electrons in our atom can only have certain energies. Actually, I should put another one here. Only certain energies. Also only certain angular momenta and a number of other things. But it's only certain values are allowed. It's kind of like your bank account isn't going to have fractional cents. You can only have 1 cent, 2 cents, 3 cents. You can't have 1.63592 cents. That's quantized. That's what quantum means. And so in atoms, our quantum theory says we can only have certain energy levels for the atoms. Often we say for the electrons in the atoms, but it's truly more than that. It's a whole system. And that quantum model then is what explains why we have the shells with different numbers of electrons that will fit in the shells. And it explains why when we had that gas tube and we wore the cool glasses, we saw only specific colors of light emitted because there's only certain energy jumps available to the electrons. And so we had the distinct line spectrum because we had electrons falling from here to here or here to here, but nothing falling a different distance. And then they give off light with the energy of the photon is HF is equal to the energy difference between where it fell from and where it fell to. You might remember my example. I was up there at the table and I drop something, it hits the table, makes a sound. Same idea, except for it's falling, instead of making sound, the amount of energy it gives off is so high that it's giving off light. That's chapter 12. Chapter 13, radioactivity. You'll see the cross-outs here, things that I do not believe we did cover. With radioactivity, part of this was, my grandma dying and going to the funeral and stuff. We need to know what it means for an atom to be radioactive. That is, the nucleus of the atom is unstable. So the nucleus will reconfigure to a lower energy state, giving off something. The thing it gives off we call radiation. That radiation can come in many different varieties. We only looked at 3 of them: alpha, beta, and gamma. Those are named in order of how easy they are to protect you from them. Alpha is very easy to protect you. Your skin will protect the rest of your body from alpha radiation. A piece of paper will provide all the safety you need. One of the homework questions I do not believe I signed, sunscreen should be enough to protect you from alpha radiation. Right? It does not take much because you have particles that are pretty big, stop quickly. Alpha particles, it turns out, are helium nuclei. Just like when we talked about acids and bases, an acid was a proton donor. Not a hydrogen donor, a proton donor. What's the difference in hydrogen and a proton? The presence of an electron. Hydrogen should have the electron with it. The proton doesn't. Same thing here for the helium nucleus. Alpha particles are a helium nucleus that has 2 protons and 2 neutrons, but no electrons. It's a helium nucleus that comes from the nucleus of an atom. So when uranium decays, it gives off an alpha particle. It loses 2 protons. You can look in the chart back there. You see uranium in the bottom row, U, last one that's dark, because it's the last one that naturally occurs. When it gives off an alpha particle, the number of protons drops by 2, so it goes from uranium with 92 protons to thorium with 90 protons. Becomes a whole new element when it undergoes radioactive decay. Beta particles, that's electrons coming out of the nucleus. And if you understood what we've talked about, then you have, but there are no electrons in the nucleus. So these electrons coming out of the nucleus is a little confusing. And it turns out you have to go through some tricky particle physics to understand that the electrons are actually being created and ejected. They weren't there to begin with.
Created in the nucleus?
They're created and ejected, yeah. Because there were no electrons in there. But what you have is, for instance, a neutron will decay and give you a proton plus an electron antineutrino. That's what's going on for the beta emission. Now, how do they know things about the alpha and beta? We go back to the Curies, and they did things like they used a magnetic field and saw that these things curved in magnetic field, telling them, hey, it's got an electric charge. And it has opposite electric charges because they curved in opposite directions. And then using an electric field, you can find the ratio between the mass and the charge. And that's how information was built up. The beta particles are intermediate for stopping. A beta particle, this won't protect me. I'm going to need something more like, this here would probably be reasonable protection from beta particles. That's wet. Then you have the gamma particles. Gamma particles are electromagnetic radiation, the same thing as light. What's different between a gamma particle and light? The energy. The gamma particles are very high energy. They're in the far ultraviolet range because you have really high energies in the nucleus compared to most things. Those are really hard to stop. Now, if you go to the dentist and you get an X-ray, that's not gamma rays because it's not coming from the nucleus of an atom. But it is also ultraviolet rays. And you worry about safety when you go to the dentist, right? They wrap you up in a lead apron or something because you want to have something to block the gamma rays, or in that case, the X-rays, which are much harder to block than alphas or betas. So that's why you've got that lead vest. Things have changed a lot. My mom, when she was a child, she loved to go to the shoe store because they had a little machine. You put your foot in there, and it would X-ray your foot and tell you what size shoes you needed. She loved that. But then they decided that X-rays are damaging, and so they don't do that anymore. And, of course, now when you go to the airport, you don't get X-rayed. You could either go through the normal metal scanner, which is using magnetic fields and seeing how oscillating magnetic field frequency changes when you go through, or you can do what I call the nudie scanners. The nudie scanners are using, they're using waves that are reflecting off of your body. So they're imaging your body through your clothes, hence my term, the nudie scanner. But what they aren't doing is using things like X-rays. So it's safe for you. It's a little invasive of your privacy. Okay, radioactive decay. You did a lab when I was at the funeral on radioactive decay. Make sure you understand what the half-life is. The half-life, I say make sure you understand, now I define it. The half-life is the time in which half of your sample will decay. So if, let's say, the half-life is 1 hour, so I have a radioactive sample that contains 1 billion atoms. If the half-life's an hour, 1 hour later, how many will it have? It'd be 500 million. Now, if I go a second half-life, how much will remain? Half of a half, so a quarter. It's not a linear decay. It won't go all of it, half of it, none of it. It goes all of it, half of what that was, half of what that was. And that's why you did the lab where you rolled the dice to see how the decay works. The reason it works that way is because it's a probability problem. There is a 50% chance that each one will have decayed. And so if you start with 10 after one half-life, each one has 50% chance of decaying. If 10 was actually a statistically significant number, you'd expect it to be half remain. So that's what the half-life idea is. That's useful because we can use that to measure times for things. If I have a sample, let's say carbon-14 has a half-life that's like 5,730 years or something like that. So if I know how much something had when it died and stopped exchanging carbon-14 with the atmosphere, and I measure how much carbon-14 it has now, I can just take the ratio between those and determine how old it is. And that's what carbon-14 dating and all of radiometric dating is using. Now, we didn't talk about the ins and outs of that. There's a lot of complexity because, who was here to measure how much carbon-14 was in something 3,000 years ago? No one made that measurement. And so we have to have some ways to impute what it started with because we can't make that starting measurement. All right, chapter 14. Actually talking about chemistry now. Right, the 12 and 13 were in the chemistry section, but they were chemistry/physics, or physical chemistry as we call it. Chapter 14 is getting very much into chemistry. So we had a chemical. What does it mean for something to be a chemical? Yeah, it's made up of elements. So what's not a chemical? No, it's a chemical. Yeah, vacuum is the only thing that's not a chemical because vacuum means nothing. So everything is chemicals. Some chemicals are useful, some are harmful. But chemical does not mean harmful. Molecule. What's a molecule?
Two more elements together.
Two or more elements bound together. So we've had plenty of examples of those. Carbon dioxide would be an example of a molecule. Change color. Element. Well, I've used element in both of my answers above. Maybe I should have had that first. What is an element? One type of atom. Same number of protons in the nucleus. If I have two protons in the nucleus, it doesn't matter how many neutrons there are. If it has two protons, it's helium. So two protons and one neutron, that's helium-3. Two protons and two neutrons, that's helium-4, which is the dominant one, the one we always talk about. A compound.
A substance consisting of atoms of different elements.
Yes. It is a molecule with at least two types of elements. And by types, I mean like if it has a sodium and a chlorine, those are two different types. That's a compound. It's not elemental. Gold, there's only one type of atom in a pure gold sample, so that's elemental because it only has one element, gold. Mixture. Multiple compounds. And in a later slide, we'll have some of these words again, and we'll have homogeneous mixture and heterogeneous mixture. What's the difference in a homogeneous mixture and a heterogeneous mixture?
One is clear. One is like one uniform, and the other one is.
Yeah, one is so well mixed that you can't tell that they're different molecules. One of them, you can tell the difference. And so, not a chemical example, but an example given just to make sure you understand the difference was the pizza. The pizza, you can see, oh, here is an olive that we need to pick off. Here is a mushroom goodness. You can see the different pieces. It's not homogeneous, it's heterogeneous. Alloys. Alloys are all by themselves here. Mixtures of metals. Alloys are metals because the metal bond is a different kind of bond, and you could put a different metal in and just takes on slightly different properties. And so we have different alloys for different purposes. All right, we had in lab yesterday having to think about how could we test the physical properties. What are physical properties? Okay, what it looks like. So color is a physical property. Its shape, its phase, if it's solid, liquid, gas. Those are types of physical properties. What are chemical properties? Okay, burning will change chemical properties. Chemical properties has to do with the bonds between the atoms. So the chemical properties has to do with the bonds between atoms. So if you change chemical properties, you change the bonds between the atoms. Physical properties are observable things like the shape, the phase, that kind of thing, color. And then name some simple compounds. So remember our simple naming rules. If you don't know, you try to take the one on the left-hand side first, then the one on the right-hand side, replace the ending with "ide." If you have multiple combinations, you can you use the prefixes like hydrogen dioxide or dihydrogen monoxide, excuse me. Yeah.
So one thing I've always had a question on is, so then when you see like a car resting, isn't that technically a chemical and a little bit of a physical change too, because you're seeing it?
You said a car?
Oh yeah, like let's just say you leave a car out and it starts rusting. That's what
Rusting. That's what I missed.
Yeah, resting.
I thought you said car resting. I was like, this is a very physics-like question, not a chemistry-like question. Okay, so you see the rust forming on a car.
The rust forming. I've wondered, yeah, that's a chemical change, but at the same time, isn't that technically a physical change?
Okay, chemical changes most often, almost always, will result in a physical change as well. But if it has as its root to chemical change, we're going to call it a chemical change. Yeah, because when we put in the phenolphthalein or our beet broth, there was a chemical change that made a physical change, something we could observe. But that would be a chemical change to make the physical change. All right. How atoms bond. The electron dot structure. Make sure that you can understand, okay, so he gave me magnesium. Magnesium is in the second column, which makes it an alkali earth metal, and it has a valence of 2. And so that means if I do the dot product for magnesium, or the dot structure, it has 2 electrons that are out there to be bonded with. And so it's likely going to form, bonds with like oxygen. Let's change the color. Oxygen has that, so it would do something like that. Now notice each of these want to have another bond. Magnesium oxide makes a nice crystal because it just keeps doing that. So make sure you understand how those dot structures work. We'll stick with simple things. Dot structures technically are supposed to work with covalent bonds, not with ionic bonds. So something like a carbon-hydrogen bond. Carbon, hydrogen. This was actually a slide from yesterday. And then those come together so that when we combine them, we have and then you see, hey, look, the carbon has a total of 8 electrons around it. It feels great. Each hydrogen has 2. 2 is actually a semi-stable configuration. That's why helium is noble. And so the hydrogen feels great, and it's just really happy. And what do we call this molecule? It is not, something like quad hydrogen carbide. It's called methane. I've talked about valence and electrons enough. I think you understand that that's important. So the valence electrons, the electrons that are in the outer shell, different types of bonds, ionic bonds. What's going on with the ionic bond?
One is donating.
Okay, you have something like a chlorine and a sodium. The sodium says, I don't need my extra electron. It donates it to the chlorine. Let me do some color coding again. So the sodium's electron goes over to the chlorine. Now the sodium is positive, the chlorine is negative. And then they just have opposite charges, and opposite charges attract. And so ionic bonds are held together because they have opposite charges. What's the difference in the ionic and the covalent? Okay, they're shared. They're cooperating. They're sharing electrons. And so a classic shared electron case would be oxygen there. It's sharing. Okay, I should have used different colors, then it'd be more clear. Missed on one. It's sharing those electrons between it so that you have a double bond between the oxygens. But those are covalent bonds. They're sharing those electrons. Yes?
For the electron dot structure, do you want us to draw them like exactly like that, like little dots? Or can we draw the bonds like as lines and stuff?
If you draw the lines, that's not a dot structure anymore. So for dot structure, yeah, you have dots. The Lewis dot structure. Okay, so that's covalent bonds. Covalent bonds, really strong. We saw yesterday, those carbon-carbon covalent bonds are really, actually yesterday, I guess it was Wednesday, really strong. Ion dipole. Now we get to things that are a little more curious. If you have an ion, like a sodium ion, and it comes up to something that has a neutral structure, that sodium ion, if it's close, it's positive, it's going to attract electrons, making the thing that was neutral now polarized. One side's negative, one side's positive. The negative side will be closer because it was attracted, but the force between charges is stronger when they're closer. So you have something that's neutral, but with the charge spread out, it actually has a stronger attractive pulse than repulsive force, and that's the ion dipole force. The ion dipole force is not holding a molecule together. These up here are between molecules, within molecules. The ones down below my line are between molecules. So the ones below the line will hold one molecule to another, like holding water molecules to water molecules. The ones above the lines are holding the molecule together, holding one water molecule together so it doesn't come apart. The ones holding molecules to molecules are weaker. but these are listed in order of strength. So dipole is a reasonably strong kind of bond, and that's what happens with water molecules attracted to other water molecules. So that relatively strong dipole force between water molecules is what makes water have a melting temperature that's reasonably high. Reasonably high, the melting temperature for water is 0 degrees Celsius or 32 degrees Fahrenheit. If they didn't have these dipole forces, it would have a much lower melting temperature. Dipole-induced dipole, same idea as ion-induced or ion dipole. Oh wait, yeah, I said ion dipole, and I described ion-induced dipole, didn't I? Ion dipole, you have a permanent dipole and an ion. Well, they just go like that. I described ion-induced dipole, which isn't here. Dipole-induced dipole, you have a dipole, something that's not a dipole, but if this is the positive end, it's going to make this so it makes a positive and negative, and then the opposites attract. Induced dipole, that's really, really weak. That's the weakest of our bonds between molecules. And that's why we have things like Teflon, the polytetrafluoroethylene, Teflon, I think I said that right, is used as a non-stick coating because you have non-polar carbon chain with fluorine atoms, and those fluorine atoms are going to have a really small ability to even have an induced dipole. So they're just not going to do much at all, and thus they don't interact. Final one here is the metallic. For the purposes of our test, let's not worry about metallic. The metallic one is kind of complicated. You have the electrons are free to travel throughout the metal, and that's what's holding the atoms together. Polar bonds. A polar bond is an uneven bond where charge is not evenly distributed. If I have like oxygen, well, of course the charge is going to be evenly distributed because it's symmetric. But if I have oxygen, hydrogen, the oxygen has a much bigger electronegativity than the hydrogen. And so the oxygen takes a lot more of the charge, the negative charge, the electron, than the hydrogen does. So an oxygen-hydrogen bond is naturally very polar, with the hydrogen having a positive net charge and the oxygen having a negative net charge. And in fact, identifying the difference between an ionic bond and a covalent bond comes at looking at the electronegativity. If the difference in electronegativity between the two atoms is less than 1/2 electron volt, then you have a non-polar covalent bond. If it's between 1/2 and 1.5, then we say it's a polar covalent bond. One side's going to be positive, one side's going to be negative. The one that's more electronegative is going to have more electric charge or negative charge to it. The one that's less than that electronegative, then will have a positive charge. If it's more than 2 electron volts difference in the electronegativity, then it's going to be an ionic bond. Then it's going to grab the charge from one and take it to the other. So the electronegativity, the measurement of how strongly it's holding its electron, is what we use to determine if it's ionic or covalent, or a polar covalent. Chapter 16, this is where I said we would have the homogeneous mixtures and the heterogeneous mixtures. We've already defined all of the things there in that first section. Solutions, concentration. I don't remember if it was homework or lab, but we had something that had a concentration in grams per liter. I think it was homework, wasn't it? Yeah, I did it in class on Wednesday. So concentration grams per liter was one concentration we did. Molarity is in moles per liter. So you should be able to do concentrations in both of those, grams per liter or moles per liter. They're not going to be the same numbers because they're not the same units. A saturated solution means that I have all of the solute that can be dissolved is dissolved. So for instance, if with our experiment where you had to determine, what was it? the one where we had the different powders and you were trying to identify them. If you just put the whole bottle of powder in your test tube, you might have some dissolve, but you'll definitely have some that doesn't dissolve. If you have some that didn't dissolve and some that dissolved, and it's in equilibrium, that means it's not still slowly dissolving, then you have a saturated solution. As much as can be dissolved is dissolved. Unsaturated means if I put more in, it would also be dissolved. And that depends on concentration, right? So saturated, it's as concentrated as it can possibly be made. Here we had what the mole means. You don't need to memorize Avogadro's number. That will be given to you. But a mole is the number of molecules that will have a mass in grams equal to the mass of one molecule in atomic mass units. And know what a precipitate is. When it rains, we call that precipitation because it's falling out. Precipitate is something that falls out when we mix things. If you mix an acid and a base, like hydrochloric acid with sodium hydroxide, when you put those together, the sodium hydroxide has sodium ions and hydroxide ions, OH negative and Na positive. The hydrochloric acid has hydronium ions, H3Os, and chlorine ions, Cl minus. Well, the Cl minus and the Na plus form an ionic bond and precipitate out as a salt. So when you mix an acid and a base, you get a precipitate that's a salt. The hydronium and hydroxide combine to form two water molecules. So make sure you understand that. Soaps and detergents, all we need to know here is that the soaps and detergents have a polar end, and then they have a nonpolar tail. The polar end is attracted to a polar molecule, i.e. water, because we wash our clothes in water. We wash our hands in water. And so the polar end is attracted to water. The nonpolar end will form very weak induced dipole forces with grime. And so those really weak induced dipole forces make the detergent hold on to grime. The polar ends make it hold on to water, and then the water will wash it away, pull it out. So that's how detergent is cleaning your clothes or cleaning your hands. Difference in soap and detergent is detergents are harsher. They have more polar molecules at the end. Almost to the end, which is good because we only have 7 minutes left. Chapter 17, how chemicals react. Make sure you can balance a chemical equation. That you can take some chemical equation and say, it should be this, this, and this. So you might remember yesterday for lab, well, the lecture before lab, I went through and said, okay, if we're going to burn octane, was it octane I did? I don't know. What's produced? It might have been methane. It was methane. That's what I did. It was methane. So let's say that I did burn octane. Octane is C8, H18, ideally, that's the relationship. So now let's balance this thing. Where would you start? Yeah, not with the oxygen because you can freely adjust the number of O2s. The only rule you have on oxygen is you're going to have an even amount. With which? Start with the C because C only appears once on each side. And so the C is probably going to be our limiting thing. And so if we put 1 here, that means we're going to have 8 there. So we have the same number of carbons. But then if we have 8 carbons, that means we have, well, let's go to the 1 here, 18 hydrogens. How many waters do we have to do if we're going to have 18 hydrogens? 9. Because each water has 2 hydrogens, That's 18 hydrogens on both sides. And now we finally just go to the oxygens. I have 9 plus 16. 9 and 16 is 25, right? Well, I can't make 25 with an integer number of O2, so what do I have to do? What I'm going to have to do is double everything. So that now I have 50 oxygen atoms, so 25 O2s. So to burn that octane, 2 octane molecules and 25 oxygen molecules produce 16 carbon dioxide molecules and 18 water molecules. So I love those when I was taking chemistry because it was just like logic, you know. You're going through saying what combination is possible. But if you're not into logic puzzles, you won't love it like I did. Know how to convert from atomic mass units to grams? We've now said that 3 times. So it is something useful to know. 1 mole of H2 is 2 grams because 1 atom of H2 is 2 atomic mass units. So if I take a mole of it, I just take the number of atomic mass units and convert it to grams. We talked about the rate of a reaction. Reactions go faster. What will temperature do to make a reaction go faster? If temperature goes up, does the reaction rate go up or down? Okay, so temperature will, if the temperature goes up, it'll increase the reaction rate. What about concentration? With concentration, you have to be a little more careful because you have the concentration of your reactants and the concentration of your products. If the concentration of your products is high, it's going to slow the reaction rate down, if not stop it. If the concentration of your reactants is high, it's going to speed it up. So it has to do with which side has the higher concentration. So if the reactants is up, that will speed it up. If the products are up, that will slow it down. Then catalysts. I spent a lot of time talking about how ozone is catalyzed by halogens. What does it mean if it's catalyzed? Or what does a catalyst do? That's right. It decreases the amount of energy needed to make the reaction occur. We call that energy needed the activation energy. So a catalyst lowers the activation energy, thus making the reaction occur much more easily, more rapidly. So the activation energy, how much energy is needed? You know, we had graphs like energy on this axis, and this axis here is reaction completion. So unreacted here, complete here, that's the activation energy, the energy required to make it start occurring. In this reaction that I drew, is it exothermic or endothermic? It's exothermic. Exothermic means it's going to release energy. How do I know it's going to release energy? Because I'm at a lower energy state at the end. So if I go from higher to lower energy, it releases the excess. Chapter 18, next to last, well, we just did organic chemistry, so this is as far as we're going to get. Make sure you actually do memorize. Bad. And Leo the Lion says grr. Bad. Bases accept protons, acids donate protons. Leo, lose electrons, oxidation. Gain electrons, reduction. What was that? It was bases. Yeah. Well, acids donate, but
Is organic chemistry going to be on the exam?
yes.
Okay.
So make sure you can identify acids and bases, what the pH is, how it's calculated, know the basics of what acid rain is, and how batteries work and fuel cells. I will see you for the test on Monday.
So I'm a little confused. So you said that. So you said convert.